Good morning, students. In this class, we are going to discuss about graph, that is weighted graph and graph representation. So already we have discussed about the graph. Graph is one of the data structure. So already we have discussed about the graph, directed graph, undirected graph. What is the example for graph? What is edge? What is vertex? Edge set, vertex set, each and everything. So in this class, we are going to discuss about the weighted graph, connected graph, then graph representation. First, connected graph. What is connected graph? In a graph, if all the vertices are connected, there is at least one path. So each and every vertex that has at least one path. That is a connected graph. So the graph G, normally we can represent the letter G to represent the graph. A graph G is said to be connected if there is at least one path between every pair of vertices in capital G. Capital G, that is graph. Otherwise, G is disconnected. Here, the two examples are there. One is for connected graph, another one is for disconnected graph. So first one is connected graph. Why? All vertices are connected with the other vertices. But in the second figure, that represents the disconnected graph because the vertex V1 is not connected with the other vertices of the graph. V1 is separated. V1 vertex, because the graph consists of vertices and edges. Vertices, what are vertices? What are the nodes are there? That is the vertices. The vertices set can be represented by capital V. So number of edges. Edges means the path between one vertex to another vertex. That is edge. So disconnected graph. The second graph is disconnected. Why we can say that is a disconnected graph means because the vertex V1 is not connected with the other vertices of the graph. So this is a connected graph and disconnected graph. Then weighted graph. If you specify the value assigned to each edge of the graph, that is a weighted graph. So the graph is said to be weighted if there are some non-negative values assigned to each edges of the graph. The value is equal to the length between two vertices. Weighted graph is also called a network. So this is the example for weighted graph. Here three vertices are there, V1, V2 and V3. It's a directed graph. Why is a directed graph? The arrow, the direction is represented in this graph. So this is a directed graph. It's also weighted graph because each edge has the value. Now V3 to V2, this edge has the weighted, the value is 8. V2 to V1, the path has weight is 7. V3 to V1, the direction V3 to V1, arrow mark. This path has the value is 4. Okay. Then what is outgoing edge? A directed edge is said to be outgoing edge on its origin vertex, that is direction from vertex to another vertex, that is outgoing edge. Incoming edge, a directed edge is said to be incoming edge to its destination vertex. If the vertex has the incoming edge, that's incoming edge. Degree, the total number of edges connected to a vertex is said to be the degree of that vertex. Then the degree in an undirected graph, the number of edges connected to a node is called the degree of that node. Or the degree of node is the number of edges incident on it. The degree of node is very important one word question. You consider this example. This example graph consists the nodes are V1, V2, V3 and V4. Is a connected graph but undirected graph because here there is no direction. So undirected graph is also connected. All the vertices are connected. In this above graph, the degree of vertex V1 is 1 because V1 is connected with only one vertex. So V1, the degree of vertex V1 is 1. The degree of vertex V2 is 3 because V2 is connected with 3 vertices. What are the 3 vertices? V1, V3 and V4. So degree of vertex V2 is 3. Then degree of vertex V3 and V4 is 2. The V3 here connected with 2 edges. So two vertices. So there are 2 edges there. So it's 2 in a connected graph. So this is the degree of vertex. Then in degree. The in degree of the node is the number of edges connecting to that node, or in other words, edges incident to it. Okay, in degree. In degree is based on the direction. Number of edges connecting to that node, that's in degree. You consider this example. This example, this is a directed graph. In this graph, in degree of vertices V1 and V3 is 2. V1 and V3 is 2 because the edge V1 has the incoming edge 2. V3 also the incoming edge 2. So V1 and V3 is 2. In degree of vertices V2 is 1 and also V5 is 1 and in degree of V4 is 0. Why in degree of V4 is 0? The direction of the edge from V4 is V4 to V5, V4 to V1, V4 to V3. So there is no incoming edge direction. So the in degree of V4 is 0. Then out degree. The out degree of a node is the number of edges going outside from that node. That's the out degree. You can calculate. You can find the out degree of the node for the above graph. Then the length of the path. The number of edges in a path is called the length of that path. Okay. Then next topic is graph representation. It's an important topic, graph representation. So graph data structure is represented using 3 representation. One is adjacency matrix, adjacency list, adjacency multi-list. So these are the 3 different representation of the graph data structure. So first one, adjacency matrix. In this matrix, the graph can be represented using a matrix of size, the total number of vertices by total number of vertices. That means if a graph with 4 vertices can be represented, the matrix size is 4 cross 4. So that matrix consists the 4 cross 4 size. In this matrix, rows and columns both represent vertices. So normally the one matrix that consists rows and columns. The matrix is filled with either 1 or 0. Here 1 represents there is an edge from row vertex to column vertex, and 0 represents there is no edge from row vertex to column vertex. So in that matrix, if you specify the 1, that is an edge from one vertex to another vertex. If you can specify the value 0 in the matrix when there is no edge from one vertex to from row vertex to column vertex. You consider this example. You consider this example for the undirected graph. This is an undirected graph because here there is no direction. So this is the undirected graph. Here in the adjacency matrix, capital G equal to V comma E. Normally the graph represents the two sets V comma E with the vertices n greater than or equal to 1. The adjacency matrix G is a two-dimensional n cross n matrix. So when you consider this graph, undirected graph, first what are the nodes are there? The rows and columns you can specify what are the nodes are there. The total nodes are A, B, C, D, E. So column you can specify A, B, C, D, E. Row you can specify A, B, C, D, E. First 0, 0. That is A, capital A, A. You have to check whether there is an edge between A, A. It's a self loop. A, A, that is self loop. So in this graph, here there is no edge A to A. So you can specify the matrix 0. A to B, yes, there is an edge from A to B. So you can specify 1. Then A to C, capital A to capital C. You find whether the edge is available from the node A to C. Yes. So you can specify 1. Then A to D, 1. A to E. Whether the edge is available from capital A to capital E. No. So you can specify the 0. So first row over. Then second row. The second row, first column, B comma A, capital B comma A. Whether the edge is available B comma A. Yes. So 1. B comma B. Whether the self loop B to B. No. So 0. Then B comma C. B to C. Whether the edge is available. No. 0. B to D. Yes. 1. B to E. 1. Then C to A. Whether the edge is available. Yes. 1. C to B. C to B. No. So 0. C to C. No edge, 0. C to D, yes, the edge is available, 1. Then C to E, no. So 0 value. Then if third row over, then fourth row, D to A, the D to A, 4 come for the fourth row. So fourth row, first column, D comma A. So D comma A, here there is an edge, 1. D comma B, DB, edge 1. D to C, there is an edge 1. You listen carefully. Here the D node has the self loop. The D node has the self loop. So D to D, there is an edge. So D to D, you can specify the value in the matrix is 1. So fourth row, fourth column. D to D. Okay, D to D, there is self loop. So D comma D, you can specify the value is 1 in the matrix. Then D to E, Yes, 1. Then E2A, then next fourth row over, then fifth row. E2A, no connection, so 0. E2B, 1. E2C, 0. E2D, S connection is there, edge is there, so E2D, 1. E2E, there is no self loop. E comma E. E comma E, the loop itself, self loop. So E node has no self loop. So you can specify the value 0 in the matrix. This is an undirected graph. Then directed graph. Directed graph, the direction is specified. So based on the direction, you can specify the value. Okay. If there is a connection, if there is a direction from this node to this node, you can specify 1. So no direction, no connection from one node to another node, you can specify 0. First, here how many nodes are there? Here also 5 nodes. Same graph, but here directed. The first graph, that's undirected. So for a directed graph, A to A, there's no self loop, 0. A to B, yes, 1. A to C, 1. A to D, A to D, A to D, there's no direction, because the direction A to D, there is one edge, but the direction is D to A, no A to D. But in the undirected graph, A to D, we can specify 1, because there is no direction. But in this directed graph, the direction, that edge has the direction, that's D to A, not A to D. So you can specify 0. Then A to E, 0. B to A, no, because here the direction is specified. So no direction from B to A. The direction, the edge has the direction is A to B. No B to A. So 0. You compare with the directed graph and the undirected graph matrix. So the directed graph matrix, based on the direction only, we can specify the value 0, either 0 or 1. Then second row, B to C, no direction, 0. B to D, yes, 1. B to E, S, direction is there, sir, 1. Then third row, C to A, no direction. C to A, the edge is from A to C, not C to A, so 0. Then C to B, 0. C to C, no self loop, 0. C to D, 1. C to E. Then D graph. D graph, D to A, yes. D to A, yes. So 1. The direction of the edge from D to A is there. So 1. Then D to B, 0. D to C, 0. D to D, D comma D. There's self loop. So 1. Okay, fourth row. D comma D, 1. Then D comma E, 1. Then E comma A, 0. There's no loop. E comma B, 0. E comma B, 0. But in the undirected graph, E comma B is 1, because there is no direction in the undirected graph. But directed graph, E comma B is 0, because the edge is, the direction is B to E, not E to B. So E to B, for the directed graph, the value is 0. Then E to C, 1. E to D, 0. E to E, 0. Okay, so undirected graph, adjacency matrix, directed graph, adjacency matrix. The adjacency matrix for an undirected graph is symmetric. The adjacency matrix for a digraph need not to be symmetric. Okay. Then adjacency matrix will require at least 0 of n square time. Then adjacency list. So linked list. In this representation, every vertex of graph contains the list of its adjacent vertices. The n rows of the adjacency matrix are represented as a chain. The nodes in chain I represent the vertices that are adjacent to vertex I. It can be represented in two forms. In one form, array is used to store n vertices and chain is used to store its adjacencies. Here the example. So what are the nodes are there? 0, 1, 2, 3. The 0, normally the list represents the node. Each node has two part, data part and link part. The data part, the node, then link part that link with the address of the next node, that link with the next node. So first graph, second graph. First graph 0, 1, 2, 3. 0th node has the connection with 1, 2, 3. First node has connection 0, 1, 2, 3. So similarly the second graph 0, 1, 2. So G3 graph. The first class we specify the graph G1 and graph G3. Okay. So next graph 0 to 1, 1 to 0. So 0 to 1, 1 to 0, 1 to 2. Two connections are there. So this is the adjacency list. Adjacency list, the link list representation, the node representation. Each node has two parts, data part and link part. So what are the nodes are there? Then represent with the link list. So this is the next another example. Here directed graph, for the directed graph. Adjacency list. What are the nodes are there? A, B, C, D, E. So the A node, A, B, C, D, E. A node with the connection B, then C. Then B node with the connection D to E. B, D and E. So based on the direction only you can link the nodes. Then C node. C node has the direction only D outgoing. C to D, not C to A. So only you can represent C to D. C node to D node only. Then D node has A. The D node has the connection D to A, D to D, self loop, D to E. So E node, here there is no connection, there is no direction from DE to other vertex. E has incoming edge, but there is no outgoing edge. B to E, D to E edge is there, but E to no edge. So E cross. Then adjacency multi-list. In the adjacency list representation of an undirected graph, each edge u, v is represented by two entries. One on the list for u and the other on the list for v. This can be accomplished easily if the adjacency lists are actually maintained as multi-list. For each edge, there will be exactly one node, but this node will be in two lists. So, adjacency multi-list node structure is there. The node structure pointer is there. We specify two vertices, vertex 1, vertex 2, edge pointer path 1, path 2. Okay, so each pointer is a max underscore vertices. So here the node has 5 paths marked vertex 1, vertex 2, path 1 and path 2. So here adjacency multi-list, adjacency, the edge 0, 1, there's 1, 0, adjacency. Here 6 edges are there. In this graph, how many nodes are there? 0, 1, 2, 3. The edges are 1 comma 0, there is edge 0 comma 1, edge 0 comma 2, or 2 comma 0, 3 comma 0, or edge 0 comma 3. Similarly, the edge 1 comma 2, edge 1 comma 3, edge 2 comma 3. Here 6 edges are there. So the adjacency list has first what are the nodes are there, total nodes 0, 1, 2, 3. Then with the node structure we can link with the adjacency nodes. That's adjacency edge. We can specify the adjacency. We know what is the matrix, what are the adjacency matrix. Here is an example for the adjacency matrix list. We can specify list two vertex, vertex 0, vertex 0, vertex 1 and vertex 2. The list is vertex 0. What are the nodes are there? Vertex 1, what are the nodes linked with? Then what are the vertex 2 linked with? What are the nodes? Vertex 3 linked with? What are the nodes? So based on this, we can specify the adjacency multi-list. Okay, so in this class we discussed about weighted graph, connected graph, disconnected graph, graph representation, the graph representation, three representation. What are they? Adjacency matrix, adjacency list, then adjacency multi list. Okay, thank you.